Okay, in this video we're going to look at something called EMFs and how they relate to voltages. Now, EMF actually stands for electromotive force, but it's not a force. It's just a voltage. It's an old-timey naming convention from the 1800s that unfortunately has just stuck, and it's a little bit confusing because, as I said, an EMF is not a force, it's just a voltage. It's a specific kind of voltage. And so we're going to talk about what EMFs are and how they're not usually the voltage that you have in an actual circuit, but they are the voltage that you start with. Okay, so here we have a circuit diagram which is indicating a battery confined in this dashed box here, and an external resistance, which is sometimes called the load of the circuit. It's just the resistor that you attach the circuit to. That could be a light bulb or whatever it is. There's another resistor indicated in the circuit, and that's the resistance inside the battery. So we have two components to this battery here. We have the EMF, or the electromotive force, and I'm not ever going to use that name again, that's the last time, but it's the EMF, it's the voltage inside the battery. And then we have this internal resistance of the battery. A battery is a physical thing. It's going to have its own resistance to the flow of current. Even though the potential difference is driving the current forward, there's still some resistance inside the battery that must be overcome. So we're going to create two different definitions. The first is the EMF itself. The EMF is defined as the voltage across the terminals of a battery when no current is flowing. So the voltage across the terminals of a battery when the current is zero, or when there is no current. Now, we can contrast that with another definition which is simply known as the terminal voltage. The terminal voltage is simply the voltage across the terminals of the battery. So the voltage across the terminals of the battery, and that's regardless of whether current is flowing or not. So the terminal voltage when there's no current is the EMF, and the terminal voltage when there is current is something different than the EMF. And specifically, there's actually a formula for that. So the formula for the terminal voltage is given by this. We have V is equal to the EMF minus I times the little r. So what we have here, this is the EMF, and that's the voltage inside the battery itself. And we have R, which is the internal resistance of the battery. Now this term, I times R, is the voltage drop across the battery when current is flowing through it. And of course, if I equals to 0, if that term goes away, then we have that the terminal voltage V is simply equal to the EMF, because that term goes to 0. And of course, if there is current flowing, we can see that the voltage across the terminals of the battery, that's what V is again. The terminal voltage is just the voltage across the terminals of the battery. That's going to be a little bit less than the EMF, because you've got this voltage drop due to the internal resistance of the battery. So let's say you have a 9-volt battery up here. If you don't have it connected to a circuit and you put a voltmeter across it, you're going to measure 9 volts. But if you hook it into a circuit and you let current flow through that circuit and you measure the voltage, what you're actually going to find is the voltage might be 8.8 or 8.9, but something a little bit less. Now, typically speaking, this R value, this little r, is a very small value. So the voltage drop, this is Ohm's law again, IR is equal to the voltage drop. The voltage drop across the battery due to its internal resistance is typically going to be pretty small. Completely fucked up. God damn it. Okay, let's consider an example now. we can look at this circuit, which has a load R, and the resistance of the load might be something like, let's say, 65 ohms, and the battery could have an EMF of 12 volts, and it could have an internal resistance, let's say half an ohm. That's a small amount of resistance, but that might be pretty typical for a battery. Now again, where I've drawn this little blue box is an indication of where the battery is. So there's the EMF inside the battery, there's the internal resistance inside the battery, and these points A and B, those represent the terminals of the battery. So coming out of the terminals of the battery, we have these wires that are connected to the resistance capital R, and that's our load. The load could be a light bulb or, whatever it is, it's some resistance, and we have a voltage that is being supplied to it at the terminal points A and B. Now those points A and B are very important because it's important to understand that the voltage at the point, or rather the voltage between the points A and B, is going to simply be the terminal voltage of the battery, which, as we just saw, was the EMF minus the voltage drop across the battery due to its internal resistance, IR. So that's the voltage from the battery side. But we also know that Ohm's law is going to apply, and A and B are equivalent to the voltage there and the voltage there, so the voltage on each side of the resistor, and that's simply going to be I times big R. And so that voltage at point A and B, or rather between point A and B, we can also say is going to be equal to capital I times big R. And that just comes from Ohm's law. So let's work an example. Let's find the terminal voltage across the terminals of the battery. We know that EMF is going to be 12 volts, but because of that little R there, the actual voltage between A and B is going to be something less than 12. So let's find out what that is. And we can also figure out what is the current going to be. So we can find also the current flowing through this circuit. So those are the two things we want to find in this problem. Let's look at that on the next slide. But essentially, this is what we're going to be using, this relationship. E minus IR is equal to I times capital R. And we'll just solve for the current and the VAB, as you'll see in the next slide. So we have E minus I little r is equal to I big R. We can solve for the current I by grouping those terms together. So we have E is equal to I big R plus I little r. I simply moved that one over there. And now we can solve for I by factoring it out. We can say that E is going to be I big R plus little r. And then we can solve for I, and we get that I is the EMF divided by the sum of those resistances. And if we plug in those values, we get that is 12 volts divided by 65 plus 0.5 ohms. And that works out to be a current of about 0.18 amps, or 180 milliamps. And that gives us the current flowing through our circuit. To get the terminal voltage, we simply say VAB equals E minus IR, and plugging in the numbers, we get 11.9 volts, which is slightly less than 12 volts, and that is the answer to our example. We now have both the current and the terminal voltage.